We are going to study the relation between the thermodynamics, probability, and entropy, and types of ensembles. These we are going to study in this unit. And coming to the introduction here, there are two types of thermodynamics. One is statistical thermodynamics and classical thermodynamics. So here, the macroscopic systems are considered in classical thermodynamics. So macroscopic systems, and in thermodynamics defines equilibrium properties of the system varies upon the size of the system. So the energy of the gaseous state depends on the temperature, volume, and number of moles gas present in the system. So it's mainly studies about the thermodynamics, mainly studies about the temperature, volume, and number of moles of gas present in the system. We are going to study. So in classical thermodynamics, we consider the macroscopic systems, while in statistical thermodynamics, we only consider microscopic systems. So the statistical methods are applicable to both in equilibrium and also in time dependent system. So statistical thermodynamics is nothing but it mainly deals with the science with application of postulates, theorems, and method of statistical, classical mechanics, and statistical quantum mechanics to description, understanding, and the solution of the thermodynamic problems. So in this, it also helps in calculating the exact value of specific heat, entropy, free energies, and equilibrium constant, etc. In coming to this concepts of distribution, here the Maxwell distribution law of kinetic energy and Planck's distribution law of energies have been discussed in the further studies. So first we are going to get into a thermodynamics probability. Probability is nothing but how likely something to happen. Probability, what is the meaning of probability? It is how likely something to happen. Whether it happens or not, that is the probability is the question mark, where how likely something to happen. So here thermodynamic probability, the Planck introduced the concept of thermodynamic probability or statistical probability. So here we'll consider a system of volume V containing total number of n molecules. So we are taking one system which is having n molecules with volume V, which are identical and distinguished. Here the total energy of all the molecules present in the system is E. The total E is represented as the total energy of all the molecule present in the system. So N is the number of moles present, where small n denotes the molecules, where E denotes the energy, and T with respect to time. So the total number of molecules in the system, how we are going to write that? Present the total number of molecules in the system is denoted as N is equal to N naught T naught. N naught is the molecules present in the energy, first level energy, and molecule present in the second energy level. So here T is the energy and n factorial, we are going to represent summation of I is equal to I to the power of I is equal to I to the power of 0, where into Ni. That is the equation 1. With the total energy of all the molecules in the system, we can write it as E is equal to N naught T naught plus E is the total energy of the system. So total energy is denoted by E is equal to N naught T naught plus N1 T1 plus Ni Ti. That is the infinity. We don't know. Summation of Ni Ti is the equation 2. So to calculate the total number of ways of distribution of molecules among the distribution of molecules among different energy levels. The molecules will be distributed in the different energy level in the system. So to calculate that, we have taken X and Y as the uh, molecules we are taken. For here they are taken as a person, but if we take it as X and Y as the molecules, yeah, it is the different energy level. So X will be having four molecules and Y molecule will, in the this the X is one energy level and Y is another energy level, where X will be having four molecules and Y will be having zero, where X shares in the next X shares the three, and one is the different molecule. So like that, the different combination means in different ratios it will be present in the different energy level. So it can be written as 4 factorial or 5 here total number of molecule present is the 4. So 4 can be shared in the different energies 4 0 3 1 2 2 1 3 or 0 4. So it can be shared in the different combinations in the system. There are five possibilities. Here we can see five different possibilities of combination of sharing of mo- molecule in the different energy level. So this is the first, second, and third, fourth, fifth. We can see five possibility combination. It is also will be known as macro state, and the macro state consists of x is equal to 1 or y is equal to 3. There are four possibilities as described in the figure 2, as x is equal to 1, y is equal to 3. Same as it is represented in the, if there is a four molecules, it is represented here a b in the x energy level, where y is having b d molecules, and next is the b, and different combination we can see four different combination are given here. In this case the total permutation combination what we can see in the keeping different energy levels, it can be showing 4 factorial. So 4 into 3 into 2 into 1. It can be represented in the permutation. And D is the 4 factorial. 4 into 3 into 2 into 1. It can be seen in the different 24. But the number also includes the permutation between the member of the house. That is the taken the example as the person's number in the member of the house. Same in this way, the molecules have been distributed. So the total number of molecules in the system is denoted by n. So here the equation 3, which is n factorial divided by W, is the thermodynamic probability. So n factorial divided by n naught is the molecules will having n naught is the molecule will have energy T naught, where N1 is the molecule which is having the energy T2. So we are writing the number of molecules in N naught factorial into N1 factorial into factorial till Ni factorial. That is the equation 3, where W represent the thermodynamic probability here. It can be written as W is equal to N factorial by pi into Ni factorial, where pi denotes the number of terms present in the permutation. So here it represents the maximum number of different ways in which a system is given state. Maybe realized, or it is the total number of possible microstate of a given macro state. So it represents the maximum number of different ways in which the system is given, means the molecule present in the given system. So some few problems are there. Here they calculate the number of ways of distributing distinguishable molecules ABC between three energy levels so that to obtain n is equal to 1. So number of ways distributing distinguished molecule between A, B, C. They are given three different energy levels. So it can be written as N naught is equal to 1, N1 is the 1, N2 is the 1. They are given. We know that from the equation 3, we are going to write n factorial divided by n naught factorial n1 factorial into n2 factorial, where you can write it as 3, sorry, here 3 factorial divided by 1 factorial into 1 factorial into 1. Well, 3 factorial is written as 3 into 2 into 1 divided by 3. So sorry, 1 into 1 into 1 divided by 1. So the answer is 6 here. There are 6 possible ways of distributing 3 molecules. 3 molecules can be distributed in 6 different ways in the system. So in the second equation, we are going in the second problem, calculate the number of ways of distributing 4 molecules in 4 energy level. There are 2 molecules in level 0. So in N naught is the 2. We should write how they are given. Uh, there are 2 molecules in energy level 0, 1 molecule in level 1. N1 is equal to 1 and N naught is the 2. That is what you are given here. And one molecule in level 1, one molecule in level 2, and level and 0 in the level 3. So N3 is the 0. It can be W is equal to 4 factorial divided by 2 into 1, 2 factorial into 1 factorial into 1 factorial into 0 factorial. This means that is nothing but the energy level. You are taking 2 molecules are present in the 0 level, in a 0 level, where 2 molecules are present in the energy level 1 and 1 molecule is present in the energy level 1 and 2 molecule, one molecule present in the energy level 2 and 0 molecules are present in the energy level 3. So we are going to write W is equal to W is nothing but the thermodynamic probability. So this may be the arrangement. So these different arrangements may be taken place inside the thermodynamic system. So W is represented as thermodynamic probability 4 factorial divided by 2 factorial into 1 factorial into 1 factorial into 0 factorial. The answer is 12 if you calculate. And next is the relationship between thermodynamic probability and entropy. So thermodynamic probability already know it is represented by W. So these are the probabilities it may take inside the system. So what is entropy here? Entropy is the measure of degree of randomness. So we are going to see the relation between the probability and measure the degree of randomness taking place inside the thermodynamic system. So here we have taken an example where it is having two different vessel. It can or container. It is shown in the figure and connected by stop cock, not stop clock. It is a stop cock. It has been used to stop. Let us imagine that containing one is having the gas with high pressure and another vessel is empty. So if you remove the stop coil, there is a strong probability. Means the molecules move from one side to another side with high pressure, or it may be equally distributed between the two different vessels. The flow of gas occurs here. And the spontaneous process may be regarded in the change from less probability state to more probability state. During this spontaneous process, both entropy and probability also increases during this spontaneous process. So you can write it as the S is equal to F into W. S is denoted as the entropy of the system. This S is nothing but the entropy of the system, where W is the thermodynamic probability. So in nature, the function of thermodynamic probability we are going to calculate here. So F of W is nothing but the function of thermodynamic probability. It can be accelerated by considering two systems having entropy S1 and entropy S2. So with the probability of W1 and W2. There is two vessels, so we are going to have two probabilities in two different vessels. So we are going to relate these two. If one vessel is having, it will be having the probability of 6 in the previous what I had told. Uh, in the different energy levels, the molecules have been distributed. That is nothing but the 6 factorial. Here, we are taking a total of S1 and S2. It is having S12, where S1 plus S2 is the equation 6. S1 and S2 are nothing but the entropy of the two systems. Yeah, this S1 and this is of S2. There are two systems present in the given figure. So W1, W2 is nothing but the thermodynamic probability of the two systems. And The probability of the combined system W12, it can be written as W12 is equal to W1 into W2. That is the equation 7. And further, in the equating in the, if I can write it as S12 is equal to F of W12. Function function of thermodynamic probability. So S12 is equal to S1 plus S2 is equal to f of W1 plus W2 when it is written expandedly. So for two individual systems, S1 is equal to f of W1, S2 is equal to f of W2. From the equation 8 can be written as f of W1 into W2. If you take it on the left hand side, if taking common, f of W1 into W2, where f of W1 plus f of W2, that is the equation 9. And next is the this will be truly in the function of logarithm, hence the above equation can be written as s of s is equal to kl ln of W10. So this is the Boltzmann-Planck equation, that is the equation 10. And next is the Stirling approximation. Here the n particles we have evaluated function in the n factorial. If small values of n, the function can be easily computed. For very large of n values, it is n values, the molecules are very less, means it can be easily calculated. For large molecule numbers, the computation will be much difficult. So ln of n factorial is equal to n ln of n minus n. That is the equation 11. Can be written as n factorial n to the power of n into e to the power of minus n. If you remove the on both sides, that is the equation 12. Uh, Next is the value of n, but it's a good approximation for log value. The This is the value, the total number of n molecules for n, when it is having 5 molecules. The direct calculation where we will get it 4.7875 from the equation. If you calculate, means 5 factorial, if you make it, it will get in the different energy levels I've previously calculated. In this way, if you calculate, you will get the value of 4.87875. If you put for large molecules, you are going to insert this formula, that is the equation 11. Ln of n factorial is equal to n ln n minus n. That is the equation 11. If you calculate by using this formula, you will get the value of 3.0447 for value of n is 5. If it is 10 means you will get 13.026. For 20 it will be 39.916. If you put this n is equal to 20 in this equation 11, you will get the value of 39.9146. And if you put 1000 or 10,000, the value are shown, it is much different to the probability of value of 6. See, calculate the value of ln 6 with and without steering approximation. So ln of 720, 2.303 log of 720, that is the value of 6.579, where if you put it in the equation 11, ln of 6 factorial is equal to ln of 6 factorial is equal to 6 ln 6 minus 6. So the calculation result is 4.750. And next is the enambles. Enamble is nothing but a simple, very large collection of identical microsystem which are allowed to interact. So your molecules are allowed to interact in the enamble. Enamble is nothing but a group. So it will having different groups for the system. Here the postulates of enamble is that there is no restriction on the nature of the content of each system, and each system may multiphase or contain dependent particles. So the number of system is enamble is very large, so the statistical approximation can be applied without any serious errors. So coming to the topic where enamble enamble average, it can be calculated by the m dash is equal to sigma of mj by psi. So epsilon. So here the property of m of the system taken over the average. There are two basic postulates for this of enamble of calculating the average values. The average of a mechanical variable enambles m over certain time t, one time t is equal to the enamble of average m, provides the system of enamble replicates the thermodynamic state and the surrounding of an actual system. So enambles of the membrane are distributed in equal probability over possible quantum states consists of with the value of n, v, and e. These two postulates you are going to understand after the explaining of types of enambles. So if you get into this diagram, you will be understanding the these two postulates. So here is nothing but the distribution of equilibrium probability over possible quanta states consists with value of n, v, and e. So here first we'll get into the types of enambles. Idaadmele you will get to know what the two postulates will be meaning. So in enambles there are three most important thermodynamic enambles. Uh, in that we can represent the interaction of one system with the another. So that is micro canonical enambles, and grand canonical enambles. So enamble is nothing but a group. So here three different groups are present: micro canonical enamble, and canonical enamble, and grand canonical enamble. These are nothing but the different environmental conditions. Like for a system anta we'll take an example alla. ಈಗ for a vessel anta. So in such a way Uh, these are the environmental conditions for the reaction of the molecule. So in that microcanonical enambles in each system is assumed to be in the first microcanonical enambles in each system is assumed to be occurred with isolated assembly of the independent particles. See, written as this membrane is denoted as rigid uh, adiabatic walls. Means rigid adiabatic walls means nothing but there is no heat transfer taking place in and out of the system. And rigid impermeable walls where the transfer of heat taking place. So N, V, and E is nothing but any here N represent the number of molecules, V represent the volumes, and E represent the energy. So there will be no transfer of energy from in and out of the membrane. So that is the rigid adiabatic walls, and rigid impermeable walls is the inner part of the surrounding in the membrane. These membranes are rigid impermeable walls, permeable walls. So in a system, it contains volume V. This what I explained previously. The system is nothing but the environmental condition. So there will be present of number of molecules with volume and the liberation of energy. So in a system consists of volume V, energy and number of molecules, and it is separated from neighbor of the rigid impermeable walls. It is separated by the neighbor of the impermeable walls. So it can be neither exchange energy nor material with the neighbors. So that is known as rigid impermeable wall, where in the rigid adiabatic walls there will be no heat transfer taking place. So that is what discussed in the microcanonical enamble. So in the next we are going to discuss about the canonical enambles. Here, if you see the diagram, you can recognize you yourself where N is the number of molecule, V is the volume, and E is the energy, and T is the temperature. So here, rigid adiabatic walls where are present inside means here this arrow is shown inside where these inside membranes, these walls are rigid adiabatic walls. That is nothing but there will be no heat transfer taking place inside the system with the neighbor also. And rigid adiabatic walls where it do not allow heat but chemical substance can pass through this. Uh, it can be separated from its neighbor by diathermic walls, and all the systems are thermally equilibrium. So this is a closed isothermal system and is also called as canonical enambles. This is a closed isothermal system and it is called canonical enamble. So next is the grand canonical enamble. Here this is an open isothermal system and it is characterized by MV and T. V is the volume, T is the temperature, such that a system is called grand canonical enambles, where diathermic permeable walls. It is nothing but the transfer of energy uh, means the heat can be passed through inside the walls. That is, inside wall is nothing but diatomic permeable walls, and outside walls are nothing but rigid adiabatic walls. Which this rigid adiabatic walls is which do not allow heat or chemical substance to pass through the other system or through neighbor. So these are the three different enambles. This is nothing but the groups where molecules are present inside the system, and it can be grouped into three different types of enambles here. And next is the Maxwell's-Boltzmann distribution law, or most probably distribution law. So here a system containing n molecules having total energy of E. Same, a system is nothing but three here. We have given three different environmental conditions such as micro canonical enambles, and grand canonical enambles. So in this system, a system containing n molecules having total energy E. So the molecules will not be in the same energy level. It will be moving from one energy level to another energy level. For molecule in energy level, it can be represented as E naught, and in energy level 1, it can be represented as E1. And the number of molecule present in the energy level 2, it can be represented as N2 and E2. So N is the total number of molecules, where N is equal to N naught plus N1 into N2 plus Ni, where summation of Ni is the equation 13, number of molecule. So the total energy of all the molecule is given by E is equal to N naught into E naught. So N naught and number of molecules in the energy level 0, and number of molecules in the energy level 1, and number of molecules in the energy level 2, such that it can be written as summation of Ni. Here it should Ei also should be written summation of Ei into Ni. That is the equation 14. And from this deriving Maxwell Boltzmann's equation, the number of assumptions are made. In the first, the molecule present in the system are identical or distinguishable. So it is an assumption whether the molecules are identical or it can be distinguished. So the molecule present in the system are supported by to be ideal. And next is the Stirling approximation, where Stirling approximation you are going to, for the n particles we have to evaluate for the function n factorial. Mm, Stirling approximation is nothing but uh, for a very large value of n molecules. Uh, it can be simply computed by ln of n factorial is equal to n ln n minus n, that is the Stirling approximation. So Ni of the number of molecules occupying in energy level Ei, the Maxwell-Boltzmann distribution equation, or most probability distribution of Ni molecule is given by Ni is equal to that is the equation 15. So here Ni is the number of molecules. This is the uh, Maxwell-Boltzmann distribution equation uh, for the N1 molecules. That is the equation 16. So N is the total number of molecule and Ei is the energy level. K is the Boltzmann constant and T is the temperature from the equation 16. And where Q is equal to summation of Gi E to the power of minus Ti by Kt. That is the equation 17. Here Q is the partition function and derivation of the equation 15 and 16 gives under Maxwell-Boltzmann's equation. If you know up till the equation 16, that's enough. That is the Boltzmann distribution equation for the most probability distribution of N1 molecules. Until here, if you write, that's more than enough. And next is the Maxwell's distribution of molecular velocity. So at what velocity the molecule is moving. So in the title itself, you can identify what's the Maxwell distribution of molecular velocity. Considering here in a gas, molecule moves in a, if we take it in a system, this the molecule moving. This is N, the molecules N moving in the direction of X with the velocity V. So if a molecule moves in a zigzag way, all the direction with different velocity. Uh, this molecule do not possess the same velocity because the redistribution of both energy and velocity as a result of collision. And after the results of collision, they will be not having the same energy. And in the next, a gas containing, that is what we explained in the system. A gas containing n molecules having the velocity v and moving in the x direction, it can be denoted as ux. So here from the plot you can see where the molecules n moving zigzagly with respect to T1, T2 and T3 are the temperature and the area of curve, this under curve, where it is denoted as the total number of molecules that you should be knowing from this plot. The plot were in molecules moving at the temperature T1, T2 and T3 different temperature having different molecules. The area curve under area is denoted as the total number of molecules present in that. And so if you get the total number of molecule means you will be getting the y-axis. What is that? Y-axis is nothing but the fractions of molecules in certain velocity with the velocity range. So n is the number of molecules, where delta ux is the velocity. So n by delta ux, you are going to get the value of the molecules moving with the certain velocity, that is denoted in the y-axis, and in the x-axis ux is nothing but the velocity in x direction. So the molecules velocity. So gas depends on the temperature. The molecule weight of gas m is represented here with n divided by delta ux, that is the y-axis, is equal to 4 pi into m by 2 pi rt to the power of 3 by 2 into e to the power of minus u square divided by 2rt into u square ux square. That is the equation 18. It is the Maxwell's law of distribution of molecular velocity. So the distribution of molecules with respect to velocity. The area under the whole curve indicates the total number of molecules present. And that is what I have explained in this. In the explanation, they are given the same. And by changing the temperature, the shape of the curve remains same, but increases of the temperature result the flattering of the maximum. The flattering will increases with the maximum temperature. And molecule possessing high velocity is due to presence of exponential factors in the 18 value. And next is the most probable velocity, and that is denoted by ux. We know that the equation 18, that is n divided by delta ux is equal to 4 pi, that is the equation 18. With respect to differentiating with respect to ux, and ux can be respect to differentiating with respect to ux, the equation 19 will get. Ux is nothing but the most average velocity of that molecules. So most probable velocity is in the previous. Most probable velocity is nothing but the calculation of average velocity of that molecule. So the velocity of gas possessed by maximum number of molecules at a given temperature, that is ux, and the average velocity ux here it can be calculated by velocity is equal to f of ux into dux is equal to 4 pi, that is the equation 20. The average velocity ux is obtained by taking sum of, then average velocity is not much important. If you go through it, there is a mathematical calculation as from the equation 18 what they have got, differentiating with respect to ux ಮಾಡಿದ್ದಾರೆ. And further, that is the equation 19 we have taken, and the molecule velocity of ux ranges from ux to ux plus dux is given as, that will be replaced here, f of ux into dux is equal to 4 pi into m by 2 pi rt divided to the power of 3 by 2. That is the equation 20. This is not much important in mathematical. And next is the root mean square velocity. And the root mean square velocity is defined where number of molecules having velocity u. So it can be denoted as u bar ux bar is equal to root of n1 into u1 to plus n2 into u2. U is nothing having the velocity u1, the number of molecules with the, that is denoted by root mean square velocity, that is ux bar. So here the number of molecules having velocity u2 etc. N is the total number of molecules presented in N is represented by total number of molecules and present in the system. This is called as ux bar into 1 by n summation of ux I square where to the power of 1 by 2. That is the equation 28. Ux is the nothing but the average velocity to find out the number of molecule of the of a molecule. So next is the relation between these. ಏನ್ ಕೇಳಲ್ಲ ಇಂಪಾರ್ಟೆಂಟ್ ಏನಿಲ್ಲ ಈ 2 marks ಇದು ಕೇಳಕ್ಕೂ ಆಗಲ್ಲ and the relationship between ux and ux bar, it's the probable velocity means expected, and this is the average velocity, and the ux bar is the root mean square velocity. This is the end of the unit. A summary of the unit you once you know, if you go through that you will get to know. ಅಷ್ಟೇ.